Hello everyone. Today we will going to see the practice questions from the chapter General Organic Chemistry. This is part 3. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. This is our index slide. We will going to see the practice questions from question number 15 to question number 21. Let's start with the question number 15. The correct order of nucleophilicity is so basically we have given some nucleophiles order for their nucleophilicity. We have to find out the correct order of their nucleophilicity. Options are most for I negative, then bromine negative, then chloride ion, then fluoride ion. Most for chloride ion, then fluorine, then bromine ion, then iodine ion. Most for fluoride ion, then chloride ion, then bromide ion, then iodide ion. Or most for iodide ion, then chloride ion, then bromide ion, and then least is for fluoride ion. You have to select the correct order. You have 10 seconds to solve this question. After that, we will see the answer. Okay, now let's see. So the correct answer is option A, that is first most is for I negative, then bromine negative, then chlorine negative, and then fluorine negative. So what is a nucleophile? Nucleophile is a chemical species that forms bonds by donating an electron pair. So nucleophile is basically a side chain or a side molecule which is attached to the parent chain, and it is a chemical species that forms bonds by donating an electron pair from itself to the main chain. Okay, so the correct order for the nucleophilicity of given halogens will be most for the iodide ion, then the bromide ion, then the chloride ion, and then the fluoride ion. We can also determine this order by seeing that which ion is having the highest capacity for the donating of electron, right? For the donation of electron. So most is for iodine. So that's why iodide ion is I negative is the most positive or most strong nucleophile, then bromide ion, then chloride ion, then fluoride ion. Okay, because you can also relate to this that fluorine is having small size, that's why it cannot donate its electron, that's why its nucleophilicity is very low. Okay, so this is the correct order, and thus our A option is the correct answer. Okay, now let's move on to the next question. Question number 16. How many chiral compounds are possible on monochlorination of 2-methyl-butane? So this is a compound name, 2-methyl-butane. Butane means total number of carbon will be 4, and at the second position one methyl group is attached. So that is 2-methyl-butane. We have asked that if you do the monochlorination, that means if you add chlorine into this compound, what will be the possible products, or you can say what will be the possible chiral compounds or chiral products which we get. How many? You have to tell the number. Options are 8, 2, 4 or 6. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. So the correct answer is option B, that is 2. So this is the structure of 2-methylbutane. You can see that in the parent chain, 4 carbons are present: CH3, CH2, CH, CH3. And at the second position of carbon, we have one methyl attached. So this is 2-methylbutane. What we are doing, we are monochlorination. We are doing monochlorination for this compound. So we are reacting this 2-methylbutane with Cl2 molecule. So we get 4 number of total compounds. First, second, third, and fourth are the names. In the first product, you can see that this methyl will directly attach to the second carbon, and to the first carbon one chlorine get attached. Okay. In the second compound, you can see that this chlorine which we have added is attached to the second position of carbon. In the third, we have seen that the chlorine attached to the third position carbon, and in the fourth we have seen that the chlorine is adding to the fourth position carbon, right? So these 4 kinds of possible compounds can be formed after the monochlorination of 2-methylbutane. But what we have to tell the chiral compounds which we get after the monochlorination. So how many of them are chirals? From the 4 compounds we get, only 2 are chirals, first one and the third one. So first and third compound are chiral. Therefore, 2 chiral compounds are possible on monochlorination of 2-methylbutane. So how we check it as a chiral compound? Chiral compound contains a chiral carbon in it. Chiral carbon is a carbon which is attached. Basically, covalency of carbon is 4, right? It can attach to the 4 atoms or different atoms. It can make bond 4 times, right? So all the 4 bonds is directly attached to different groups of molecules. Okay, that is the chiral carbon. So if you see, for example, in the first compound we get this star carbon is having 1 bond with hydrogen, 1 bond with this group CH2Cl, 1 bond with this group CH2CH3, and 1 bond with this CH3 group. So you can see that all the 4 group bonded with the carbon or star carbon are different. One is CH2Cl, hydrogen, CH2CH3, and CH3. All are different. That means this carbon attaching to different groups is a chiral carbon. Similarly, if you see in the third compound, this star carbon is directly attaching to the 4 different groups. That's why it is a chiral carbon. You can see one is chlorine, another group is hydrogen, another one is CH3, another one is the CH3, this whole. Okay, so that's why it is a chiral carbon. In fact, you can also check in second and fourth. If you see in the second one, this carbon is having 1 Cl, 1 CH3, again 1 CH3. So these are 2 same molecules which is directly attached to this carbon. That's why it is not a chiral carbon. In the fourth one also, if you see any carbon, if you check any carbon, every carbon is attaching with the 2 same types of side chains or side atoms or molecules. If you see this carbon, one is hydrogen, one is CH3. Again, the CH3 is present, so 2 times CH3 will come, right? That's why it is not a chiral carbon. So only first and the third compound is our chiral compound. Therefore, 2 chiral compounds are possible on the monochlorination of 2-methylbutane. Okay, that's why we have a correct answer as 2 in the option B. Okay, now let's move on to the next question. Question number 17. The question is, which one of the following is most stable? We have to tell from the options A, B, C, and D. We have given structures. We have to tell that which one is the most stable structure, or ion, you can say, because positive charge is present. First one, options are A is this alkene, cyclohexene, and this one methyl group is present at first position. So 1 methyl cyclohexene and this positive charge on this 1, 2, 3 third carbon. In the B option, we have this cyclohexane and this you can say cyclohexane. Okay, cyclohexane having a positive charge at the first carbon. In this also we have cyclohexane having positive charge on the third carbon, and in this also you can say nitrocyclohexane and positive charge at the third carbon. Okay, so you have to tell that which among these four carbocations the most stable will be. Okay, you have 10 seconds. After that, we will see the answer. Okay, let's see. So the correct answer is option A, that is this compound. This compound is the most stable from all the given options. So, due to the presence of electron releasing group or electron donating group, CH3, methyl, and resonance effect, it is the most stable. You can see that this is the structure and this is the methyl group, which is an electron donating group attached to this double bonded carbon, and positive charge is present at this third position of carbon, right? So what will happen, this CH3 group shows the electron donating group effect. Okay, this is the electron donating group, strong electron donating group, and also resonance will happen, like this double bond will go here and this positive charge will come here, right? Then this CH3, as it is a electron donating group, it will donate the electrons to this positive charge, like present at this carbon, and the carbon get satisfied with the enough number of electrons, and this molecule or this carbocation get stable. So due to the two regions that it is attaching to the electron donating group, releasing group, and due to the resonance effect, it will show this is the most stable carbocation among the given options, and thus option A is the correct answer. Okay, let's move on to the next question. Question number 18. The order of stability of the following carbocations is. So we have given some carbocations. First one is this, in which 3 carbons are present. Between the 2 carbon we have double bond, and the third carbon is having positive charge. This is the second carbocation, in which no double bond is present, 3 number of carbon are present, and in the third carbon positive charge is present, and in the third carbocation we have a benzene group direct, and one CH2 is attached to this benzene ring directly, and carbon in the CH2 is having positive charge on it. So these 3 types of carbocation we have to tell the order of stability, that how much stable and which one is the most stable and which is the least stable. We have to tell the order of stability of these carbocations. Options are: third is more stable, then second, then first is least stable. Second is most stable, then third, then first is least stable. First is most stable, then second, then third is least stable. Or third is most stable, then first, then second is least stable. So you have 10 seconds to think about this question, and after that we will see what will be the solution. Okay, let's see. The correct answer is option D, that is third is more stable than first and then second. So the order of stability of carbocation will be, this is the third carbocation, which is known as benzyl carbocation. Why? Because it is more resonance stabilized. In the benzene ring shows the most stable resonance form, right? And it will show the resonance effect more stably. That's why the benzyl carbocation, due to the more resonance stabilization, it will be more stable. Then at the second place, allyl carbocation will be there, double bond is present, that's why we are calling it allyl carbocation. Here also, due to the resonance effect, it is stabilized, but the allyl carbocation is having less stable resonance than the benzene ring. That's why it is in second position. And at the third position of stability, we have propyl carbocation, and it is stabilized by plus I effect. Like 1CH3 is present, so it will donate the electrons to this positive charged carbon and it will get stabilized. So due to plus I effect, the propyl carbocation is stabilized, and this is the order of stability for these given carbocation. The most stable is benzyl carbocation due to the strong resonance effect. Then the allyl carbocation at the second position because the resonance effect is lesser than the benzene, but it is effective. And at the third position, we have propyl carbocation because no resonance will happen here, but plus I effect is present, which is less, which we will give less priority than resonance. So it will be at third place. So this is the correct order for the stability of the carbocations. And in the question, we have given benzyl carbocation as the third, allyl carbocation as the first, and propyl carbocation as the second compound. That's why the correct order is most stable is third, then first, and second. And thus, D option is the correct answer. Okay. Now let's move on to the next question. Question number 19. Which among the following free radical is most stable? So we have given some options A, B, C, and D, and we have asked that which free radical is most stable. You can see A is this cyclohexene or methyl cyclohexene as a free radical, and then this second one as a free radical, this methyl group as a free radical, and this is a allyl group as a free radical. So you have to tell which is most stable free radical. So analyze it for 10 seconds. After that, we will see the answer. Okay, let's see. So the correct answer is option A, that is this 3-methyl cyclohexene free radical. So among the given free radicals in the options, allyl free radical is stabilized by the resonance. Again, here resonance will happen. In the cyclic structure, resonance is more stable. That's why in this structure, resonance will happen and it will get stabilized by the resonance, and thus the compound A is more stable than the rest of the options. Okay, and thus A option is the correct answer. Okay, let's move on to the next question. Question number 20. Which is the most stable carbocation? Again, we have given some carbocations in the option. We have to tell which is most stable. In the A option, you can see which we have CH3, CH2, CH positive and directly attached to benzene ring. Or benzene ring having positive charge, benzene ring attaching to C positive CH3, CH3, benzene ring attaching to C positive H2. So you have 10 seconds. Think about this question and then we will see the answer. Okay, let's see. The correct answer is option C. That is this. Benzene is attaching to carbon having positive charge directly attached to two groups of methyl. So basically, this is a tertiary carbocation. That's why this is more stable, because you can see two electron donating group is directly attached to this carbocation carbon, right? Carbon having positive charge is directly attached to two electron donating group. That means electron can be donated by this methyl, either by this methyl, and this carbon can get stable. Also, resonance effect will be effective here due to the presence of benzene ring. That means we have three factors for the stability of this carbon having positive charge. That's why it is a tertiary carbocation and hence it is most stable. And thus option C is the correct answer. Okay, move on to the next question. Question number 21. the most stable carbanion is. Now we have given carbanion. We have to tell which is most stable. First one, phenyl CH2 negative. Second one, MEO connected to benzene ring connected to C negative H2. NO2 connecting to benzene group connecting to CH2 negative. And in the D option, benzene ring connecting to CH2 C negative H2. You have 10 seconds. Think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option C. That is benzene ring directly attached to NO2, directly attached to C negative H2. So, electron withdrawing group, EWG means electron withdrawing group stabilizes carbanion. Carbanion means carbon having negative charge. Carbocation means carbon having positive charge. So, electron withdrawing group, what will happen? It will withdraw the electrons and remove the negative charge so that it will get neutral and get stabilized, right? And NO2 is an electron withdrawing group which is directly connected to this benzene. That's why both by the minus inductive effect and minus resonance effect, this will get stable. This carbanion will get stable, and hence C option is the most stable compound. Right, because NO2 is an electron withdrawing group. It will withdraw this negative charge, withdraw this electrons and gets the CH2 stable, and also resonance effect will show by the benzene ring. It also gets stabilized the CH2 negative charge, and that is why due to these two reasons, major reasons, option C having this compound is the most stable carbanion. And thus, C option is the correct answer. Okay. Thank you.